Yeah.
All right, we're live. We'll see how this all goes.
All right, this is Justin Rosenberg, and welcome to Kansas City Java User Group. And the first time since we had the pandemic that we're doing it in person. I would show you the hundreds of people here, but we'll just continue. I would like to thank our sponsors, CRL. CRL pays our meetup costs, and yeah. Right. Okay. So we have a lot of open positions. So CRL Corp, we have remote application developers 1 through 3, and sysadmins, and a software architect, and desktop services. Anything you do, we'll hire you. Java news for the month. We got JDK 19, branch from Maine. It's got third preview of pattern matching, and it's got the first preview of virtual threads. That's the Project Loom, and that's really, really cool, and it will be a lifesaver when it gets live. And structured currency, Panama, first preview of foreign functions and memory API.
So it's like an improvement upon how to interact with native code.
Okay.
So it's one of those, if you kind of work in that area, it's a big improvement. If you don't, like many web developers, doesn't mean anything.
Right, but that Project Loom will really help with the reactive programming.
Yeah, structured concurrency is also big with Loom for actually being able to spin up lots of threads to spin up that. It's just going to be a way of handling that. So.
Yeah, and that's Billy Conrado for people who are interested. There's a YouTube video. I suggest you watch it. Releases, we have test containers 1.4. There's no releases. We just do whatever.
Yeah.
All right, KCDC. I implore all of you to come to KCDC. I'll be there August 8th through 10th.
Yeah, I believe also the agenda has just been released as well.
Oh, really?
We also have a really good Java track this year, so check it out.
Cool. JConf is in September 26th through 28th in Chicago. And Java 1, I think they should just send us. I've been to Java 1 one time, and I'd love to go again. And Las Vegas, I mean, hey.
Exactly.
Anything we miss? Any announcements from the crowd? All right.
I guess the one thing is you want to mention the camera.
The camera, yes. This camera has 30 minutes, so we might have to do a little bit of switching.
Just may go out.
But we have the camera there to introduce. And this, is you volunteer to speak. You can provide feedback. Join a Twitter.
Oh, I think I forgot. I thought
come up here.
No,
yeah. I don't know how good they can hear you.
Yeah. Sorry, I should have been up here earlier. One quick also thing is that we are looking for volunteers for Kansas City Developer Conference, and so it's a free ticket to get in, and it's only maybe a few hours of work to maybe help register people and something like that. So, but anyways, if you're interested, email gabby@kcdc.info. And yeah, like I said, that's a good way to kind of get involved in the local community and then also get a free ticket to KCDC.
Thanks, Billy. And okay, now I hand over to Dave.
Thank you.
He's a wizard, and he'll tell you about it.
Not going to be telling you that. All right, let's try this here. Does that sound okay? How am I going to know? Somebody out there in the ether tell me if it sounds okay. All right, so my name is Dave Klein. I'm a developer advocate with Confluent. And Confluent is a company that was founded by the original co-creators of Apache Kafka. We don't own Apache Kafka. Apache Foundation owns Apache Kafka. So it's important to point that out. Apache Kafka is an Apache project and supported by the community. Confluent does provide a lot of support, and we're heavily involved in the Kafka community. We hold a lot of Kafka meetups around the world and host those, as well as sending people like me out to speak at Java user groups and elsewhere. And today we're going to be talking about Kafka Streams basically, but we're talking specifically about how to take advantage of our data while it's in motion, rather than our traditional model of just taking data from a database, doing something with, putting it back in a database. So we'll talk a bit more about that, but that's our presentation. There's my email address, Twitter handle, LinkedIn, any way you want to contact or connect with me, feel free. And let's get started. So what do we mean by data in motion? We've heard the terms data, data at rest, data in transit, maybe normally in terms of thinking about encryption or things like that. But what we're talking about here is how are we working with our data? Like I said, well, there's also that data in motion too. But the traditional model is data comes into our systems through an application, some kind of interface, right? Some edge. And then first stop is the database. Maybe some validation first, but then right to a database. Then we'll pull it from the database and start doing something with it. And what I'm proposing and our company is proposing is that taking advantage of the data while it's still in flight, as it's coming into our organization, or as it's moving from one part of our system to another, there's a lot of value there that we're leaving on the table by just doing things directly from the database. So there he goes. And so what is it good for? And so here's just a list of some things that some of our customers are using it for. And when I say data in motion, another word you might think of for this is just streaming data. That term gets a little bit vague sometimes because it could be streaming movies or streaming things like that. So we're using the term data in motion just to specifically differentiate between data at rest and a data store. So using it for Customer 360 is pretty popular. Recommendation engines, that's a really important one because recommendation engines, if they're using older data, they're not going to be as valuable as if they're using the current data that's being generated while customers are browsing your site. And I won't go through all these. I want to mention a couple specific ones that I've interacted with myself. One is the fraud detection, which is a very common use for this. And so if you probably had this before where you're going to use a credit card somewhere. For my situation, it was at the gas station where my family was traveling across country. Right, so I'm in a town I'm not normally in. Credit card picks that up. Say, you don't normally use your card here in wherever, Biloxi, Mississippi. And so it declines it. And that's fine. I've got other cards. I use something else and I get through and I get my gas and move on. The next day or maybe that night at the hotel, I get a text message or an email from my credit card company saying, were you trying to use your card at such and such location? So, yeah, I was, but that doesn't really help me now. And so later on a more recent trip, I did the same thing, used my card, a different credit card, but I used this card, it got declined, and as it was being declined, as I'm reading the message on the pump, my phone's buzzing. I pull it out, it's a credit card company saying, are you trying to use your card at this location? I tap 1 for yes, and it says, okay, it's all clear now. I swiped it again, it worked fine. So they took care of the issue right then and there. So they still protected me, and the fraud protection is for my benefit, theoretically anyways, and so that's great, but they did it without inconveniencing me like it was doing before. And you can see the difference there. The ones using the data in motion, they're reacting to that data as it's being generated. Others are pulling that data out of a database and running through their process and sending me an email the next day. The other one that I've noticed this with really stark contrast is with customer loyalty programs. And these aren't a huge deal. They're not really, no one's life is depending on customer loyalty programs, but it does make a big difference in the experience your customers are going to have with you. So, for example, I stay with a certain hotel chain. In fact, I'm staying with them right now tonight. And tonight I'll stay at the hotel, and about 4 days from now, I'll get the points for that stay will show up in my account. Right, which is fine. I don't need them instantly, but it's a little bit inconvenient because if I'm with my family on a road trip, we're stopping each night. Sometimes it'd be nice to get the points one day, use them the next place we stay. Right, you can't do that with this program. Well, but by contrast, the airline I fly with, when we land the plane, I go out to the terminal and I can check my account, and the miles for that flight are there already. So again, one of those is taking advantage of data in motion. Others are just using it, pulling it from the database and dealing with it later in batch mode. So, and these other different systems, fleet management, keeping track of vehicles while they're traveling, where they're at, how their fluid levels are, temperatures, things like that can be sensed on fleets, on vehicles in a fleet, and reacted to in real time. Real-time payments is another very popular one, and again, one that you really needed. That one has to be real-time, obviously, it's in the name, but imagine doing that in batch. You send somebody with somebody in Zelle and they don't get it. Well, actually, that does happen, right? Sometimes you'll use something with Zelle or Venmo and it takes 2-3 days for it to show up. I'm not sure why it does sometimes in others, but But those things are important to be able to handle quickly, and that's what we're aiming for here. So before we talk more about how we're going to do this with Kafka Streams, are people familiar with Kafka here at all? Apache Kafka? A little bit? Okay. I wasn't sure, and I don't know about people online, so I did include a little bit of a primer in Kafka here. This is my own little book here called Kafka the Diminutive Guide. I didn't want to try to compete with Kafka the Definitive Guide, so I made my own. But it's just a simple primer on what Kafka is. It'll take about 10-15 minutes. So if you're already familiar, this will be a review for you. But in case anyone's missing out on this, it gives you some background as we talk about the rest of it. So at its core, Kafka is just a log. It's an immutable, ordered, append-only log of events. Right? So events get added into the log one after the other. They're there forever. If you read that event, it's still there later. Somebody else can read it as well. It's not a queue. Things don't get pulled off of it as you read them. A lot of people make that mistake and confuse those things. It's just a log. It is ordered. The order never changes, and it's immutable. So once an event lands in a log, it cannot be removed. I mean, there's ways you can cheat the system and do it, but by default, it's not removed. Things can drop off the end based on time or storage size, but that's configurable. We can control that. So you can keep your data in a Kafka topic forever if you want to, if you have enough space. Now, there's also tiered storage where there's a hot data set kept on disk, and then older data is moved off to an object store like S3, and then you really can keep your data forever. But that's a separate topic. See what I did there? Okay, so here's a picture of what an event might look like in Kafka. Now, in Kafka, in a Kafka topic, which was the log we're referring to, it's just bytes, right? And it's a very efficient binary format that Kafka uses to store the data. So everything has to be serialized 2 bytes and deserialized from bytes to whatever you want it to be. But in general, when we're working with Kafka, we're going to use some type of a data format like JSON or Avro or protobuf, or even just your own structure that you have serialization and deserialization for. So, but this is a typical example in JSON. Your key, the 2 main components of a Kafka event are the key and the value. The key is usually a simple data type like a string or a long or maybe a UUID. The value is usually more complex, and that's your payload. It's basically that's your object data. And this, like I said, this case is JSON, and you could use other formats as well. Now the key is optional, but it's important, and we'll see that here in a bit. So here's a little bit more accurate picture of a Kafka topic, because most Kafka topics are made up of more than one log, each of them called a partition. So this topic has 3 partitions. Each of those is its own ordered, immutable, append-only log. And as events are written to the topic, they're distributed. The first set of events we're going to watch here are events without a key. And if events don't have a key, they're distributed across the partitions of the topic relatively just evenly, basically. You used to use round robin. Now it uses another algorithm that's a little more efficient, but the goal is to keep them distributed evenly across the partitions. And that works really well. It does it really well, keeps it from getting a hot partition. But as you can see here, you don't quite have the ordering you might want. So as the data is consumed and processed from these partitions, there's no guarantee that 101 might not be processed before 100. Because they're in separate partitions, they could be processed at separate times. We can guarantee the order of processing for everything in a given partition, but not across multiple partitions. So the key to handling that is to use a key. If you use a key, what happens then is that the value of the key itself, there'll be a hash created from the value of the key, and then that hash will be modulated with a number of partitions. So in this case, 3, and that's going to give every key is going to be assigned a value of 0, 1, or 2. And then that key will always land in that partition, 0, 1, or 2. And now you'll have a guarantee of ordering. So the A1s here, which are the 100 series, will always be in that first partition, and then so on. So now we can be sure that 100 will be processed before 101 and then before 103, right? We wouldn't have that guarantee otherwise. But as you can see, this approach doesn't necessarily give us as even a distribution on the partitions. This is especially something to think about if you're using something like a customer ID for your key, and if you have 1,000 customers, but 2 of them represent half of your business, that's not going to be a good situation, right? So you can very easily create a custom partitioner. It's just a Java class you extend in the configuration file. Say, hey, use this class for the partitioner instead of the default, and it'll use that. So you can do custom logic to determine which partition things go to, or you can choose a more distributed key. So that's how there's that. Yeah. Okay. So that's that. So then the thing that puts the events onto the topics is a producer. I'm back to just showing one partition here, but it could be multiple. And the producer is the one that has the smarts to know which partition to write to. It also handles things like, draw a blank on the word again, compression. So there's different compression algorithms you can use to make this data even more tightly stored in Kafka. And so the producers will do the compression for you as they're writing the data. So the producers have a lot of smarts. The broker, which is these topics reside in the Kafka broker, and the broker is pretty dumb. It's meant to it's very simple and fast. It's not meant to do a lot of logic. Most of the logic is going to be on the clients, which is the producers and consumers we're looking at now. So the producer just writes the events to the topic one after another. The consumer, which is completely decoupled from the producer. I should mention both of these are part of the Kafka client library. The Kafka client library is just a Java library. The one that ships with Kafka is a Java library. There are client libraries in most other popular languages now that you can download separately for Python, Go, Node.js. I think someone even just wrote one in Rust, but they're there for what's that? C#, yeah. Well, yeah, the .NET one works all across the .NET languages. So, yeah, and Confluent specifically supports the ones for .NET, for Python, and for Go. And there's a lot of community-supported ones for lots of other languages. But in here, we'll be talking most about the Java clients. So the producer and consumer are both classes in that client library. And as they do their work, they're completely decoupled. They don't know anything about each other. The consumer doesn't know who's putting these events on the topic. The producer doesn't know who or if anybody's consuming them. And that's really important for keeping our services decoupled and for not allowing one system to affect the other downstream. So the consumer, as it's consuming these events, I don't even like the name consumer because, like I said, it doesn't really consume the events. It reads them and it processes. You do whatever processing you want with them, but the events stay there. They're not consumed off of the topic. They're still there for somebody else to use again later, or for you to replay if you want. But the consumer that you're running, it will keep track of where it's at, which events it's actually already processed, and it periodically will store that this number here where each event resides is called the offset, and the consumer will store the offset of the one that's most recently completely processed, and that'll be the committed offset. And then if the consumer goes down, the producer, first of all, will keep on going. It doesn't care. At this point, you will see there's a metric that you can watch for called consumer lag, where the broker will say, hey, there's more events landing here that are being consumed, and that's just something that a trigger for you to check and see what's going on in your system. But the producer won't stop because of it. It won't. It'll just keep on doing its work. And then when the consumer comes back online, it will use that committed offset to figure out where it left off at, and it'll pick up right at the same spot there and continue on. So you never lose data, you never skip data. And those are two key things with Kafka. That's if you're using it well and configuring it properly, it's very difficult to ever lose data with Kafka or to skip processing.
Does the consumer have to store the offset, or is Kafka?
The consumer is actually storing the offset in another Kafka topic. I'm sorry, I didn't understand the question. Yeah, so this offset here is a value that you can change. So you can reset your offset back to the earliest or to a specific one. So you can seek your offset by timestamps. You can seek to a specific offset like 24 hours ago, and you could change the offset to there and then start up again. It'll replay from there. That's one of the key advantages to this log rather than a queue, is that you can go back and replay data. So if you find a bug in your code, fix the code, reset the offsets to a time before the bug occurred, and then replay forward. You can send, if you have error, that's something you'll have to do on your own, but it's a common pattern is to watch for poison messages and write them off to like a dead letter topic. Okay. And then you can handle those manually. There's nothing built in to do that for you, but it's easy to do. All right, so that's the producer and the consumer. Now, I could mention they're completely decoupled. They don't know anything about each other, but they do need to know about and agree to the way they're handling the data, right? So the producer needs to serialize this data to bytes, and the consumer needs to deserialize that from bytes back to something that it can use. And so the best way to do this isn't required. You can hard code the deserialization and serialization rules in your producer and consumer if you want to, but the suggested way and the best way to do it is to use a schema. And Kafka has support for Avro, Protobuf, and JSON schema currently. And so using a schema the producer will use that schema to do the serialization, and then the consumer will use that schema to deserialize what it receives, the bytes it receives back to the right kind of object. And then the schema registry, which is another piece that's not part of Apache Kafka, it's from Confluent, but it's free to use even for commercial purposes. And I think the only thing you can't do with it is use it in a cloud offering competing with Confluent, but any other use is fair game. And so the schema registry, it will keep track of schemas, and it'll handle communicating the schemas between the producers and the consumers. So what happens here is a producer will, and it's really easy to use. All you do is you give the producer, in the configuration of your producer, you give it the location, the URL of your schema registry, which is a separate application that you run. And then it will automatically start working with it and it'll communicate with it. So when a producer is going to send a message that has a schema, it will first send that schema to the schema registry. The schema registry will return an ID, a unique ID. The producer will cache that ID, and then it will prepend that ID to every event that it writes. So when it writes an event, the first 4 bytes are going to have, the first 5 bytes, the first byte's a magic byte that tells it there's a schema. The next 4 are the ID of that schema. And so every event that this producer writes will have that ID in it. And then the consumer, when it gets an event, it's going to look and say, oh, there's a schema ID. It's going to call the schema registry, give it that ID, get back the schema, and it'll use that to deserialize, and it'll cache that schema. So these calls between the producer and the consumer and the schema registry only have to happen when a new schema is introduced or when a schema is changed. And schemas do change, and the schema registry helps us with that as well. Schema registry, you can set compatibility rules. So you can tell it, I will only allow changes that are backwards compatible, or forwards compatible, or both. And you set these rules, and the schema registry will enforce those rules. So if you try to make a change to a schema that doesn't meet the rules you set, it'll throw an error. Also, if a producer tries to produce an event to a topic and the schema, the structure of the data doesn't match the schema that it says it's using, the schema registry will block that as well, or it'll throw an error. So actually, the broker does that, but using the schemas in this way will give you a lot of protection from corrupting your data and make it easier for producers and consumers to communicate. So again, not a required piece, but it's a really important and valuable one. Okay, the next bit, I think this is the last bit for our primer, is consumer groups. And consumer groups are amazing. Consumer groups allow us to have multiple instances of our consumer application share the data, share the workload in a topic. The unit of scale for this is the number of partitions. So the data in a single partition cannot be split across more than one consumer instance of the same application. You can have multiple applications hitting it, that's fine. But for the same application, you can't split it further than just the partition level. So the way it works is you use a group ID in the configuration of your consumer. And then once you have that there, But I'm sharing my screen. Whoa. All right.
All right,
Are we good?
we're back on.
Hey, we're back. All right. So as we're talking about the consumer group rebalancing, so in this example we had here, this partition 3 here is being worked on by app instance 2. So when we go to add these new ones, what will happen is app instance 2 will finish what it was on, commit that offset, and then that offset will be used by app instance 4. It'll be app instance 4 will just do the same thing as if it were app instance 2 and shut down and restart it again. It'll pick up where that one left off. So it won't skip a beat. It'll just keep on going, and now we'll spread the load across these 4 partitions. At this point, we could add a 5th instance of our application, and this is done sometimes, especially if your applications have a bit of a startup time, and basically it's a hot standby then. So it'll sit idle, it won't do any work, but if one of these dies, then that 5th one will jump in and take over, and it'll all happen automatically. And when things slow down again, we can always scale back, and again, the rebalancing is done automatically for us. So the consumer groups is a very powerful and helpful tool for this, because a lot of applications will be running with 100 instances and hundreds of partitions, and so it's not uncommon to have that. Only to the extent that you can't split them more. So that's the limit of your scale. You can only go up to the number of instances as you have partitions, but otherwise there's no, and they don't have to be. In diagrams like this, you'll always see them in even things. So I have 2 and 4, but it could have been 3, and it'll give. If I had 3 instances, it'll give two partitions to one, and then 1 each to the others. So it'll always just balance it as close as it can to evenly. So with that in mind, and also we're talking about the keys we talked about earlier too, and I hope I don't want too much time here, but it's really important to think through when you're creating a new topic, how many partitions you're going to want to have, and you want to basically make it a little bit more than that, maybe even double that, because changing the number of partitions after you have data flowing through them is really a bad thing to do. If you're using a key and you increase the number of partitions, then that changes off all of the partition assignments for the keys. So new events with the same key will start going to a different partition than the old ones were, and now you've lost your ordering guarantees. And if you're growing, if you're shrinking, you can end up actually losing data if you just drop partitions and don't migrate in some way. So if you do ever need to change the number of partitions on a topic, the best thing to do is create a new topic with the new number of partitions and then migrate the data over, and then it'll all work right. So, but having more partitions is valuable because it does allow you to increase your scale horizontally if you need to. And this comes into play most with consumers, less so with producers, because producers generally just send the data and they can do it really quickly and you don't need as many of them. But processing normally takes longer depending on what we're doing with our data. And so you're normally going to want more consumers than you have producers. Right. So that's that. And the other thing is to point out, and I mentioned this earlier, but you can have multiple consumer groups. Different applications can be reading from the same topics. They can be reading at different places and different paces, and they're completely independent. They don't affect each other because the data is just there in the log for anybody to use. And that's a really valuable point too. I don't get into it here, but I have another talk on event-driven systems with Kafka, and that's really helpful there, is that you can add new systems into your like new microservices into your architecture that can work from the same data that your existing applications are using or the data that they're generating, and it won't affect those at all. Right? So you can add on auditing applications or analytics applications that will take that data that's being generated and read from the same topics without affecting your current processing. All right, so that was it for the Kafka primer. So now back to the concept of data in motion. So we're going to be looking at mostly at Kafka Streams here, but I want to just kind of show how this is all built out. We saw the consumer and producer API. And with those, we could do pretty much anything. So we could do full-blown streaming applications with the producer and the consumer. We would have to do a lot of work ourselves to do that. There's a lot that comes into when you start working with data, especially if you're doing any kind of stateful aggregations or transformations on your data, then it's really tricky to keep track of all that. So we have, wrong direction. We have the Kafka Streams Processor API. And this is, again, as part of the Apache Kafka project. And what it does is it's a low-level API that allows you to build, to do transformations and aggregations and things like that on your data as it's flowing through the system. So as every time an event lands in a topic, if it's an input topic, it'll do whatever processing you set up to do, and then produce that to output topics or to just some downstream system. But it's not the easiest API to use, and so on top of that, they've built. I keep on the wrong direction. See, my stack's going up, so I'm using my up arrow, but I'm supposed to go down. Like the AC issue we had earlier, right? So on top of that, there's the Kafka Streams Dsl, and this is what we're mostly going to focus on today. And this is a really nice fluent DSL that has several built-in functions for doing the most common aggregations, transformations, joins, things like that you're going to do with streaming data. It's built on top of the Kafka Streams Processor API, which is itself built on top of the producer and consumer API. And this is important because when you build a Kafka Streams application, you get that consumer group handling that we saw earlier. You get that in your Kafka Streams application as well, because it's all built on that same API.
Are there any clients for like Kafka Streams, or it's not required? Like use clients for CB producer?
Well, that's the thing. So these are all clients. So Kafka Streams is just another Java library. So which is an important thing to point out, and so I get to another thing shortly that isn't, but these are just libraries that you can include in your applications. So normally you'll have an application like a microservice that it will do some stream processing for you, and you'll just include that library and start using that code. And you can intermix it with your own code to do whatever you want. The one thing it's advised not to do, people sometimes still do it, but you generally on a streaming application, you don't want to make calls out to external applications like HTTP calls out, because then those can throw off the timing of your streamed application, because you don't know when the results will come back. Yeah, these are just libraries that you can include in your applications. This next one up, which is built on top of Kafka Streams Dsl, is K-Sql Db. And K-Sql Db is an application that you run. It's not a library. It's built on using Kafka Streams, but it allows you to build streaming applications using SQL. So you have these SQL selects that actually are streams. So that rather than just giving you a single result set back, they give you ongoing results back. So I'm not sure what you mean by
is it asynchronous?
yes.
Okay.
So you'll create a query, and you create a stream based on a topic, and then you select from that stream. You can use a where clause or something like that, and then just leave that running, and any new events that land in that input topic will show up in your results set. So it's often used for things like dashboards or for sending data to analytics engines after you do some manipulations with it. It's also being used for building machine learning pipelines. So you do some of your data cleaning and shaping in K-Sql Db, and then send that to another topic, which gets consumed and fed into a machine learning model. So, and just like with most things like this, the lower level you go, the more that you can do, but the more work you have to do. So each step up is you lose some. So like, for example, the Kafka Streams DSL can't do everything that the Kafka Streams Processor API can do. The nice thing is you can jump from the DSL, you can drop down into the Processor API, and if it's something that doesn't do for you, you can jump into the low level code and do it yourself. And even from there, you can even drop right down to the producer or consumer and handle things specifically if you needed to. So this one, not so much. You can't drop down to these ones when you're in K-Sql Db because it is a separate application. These are just libraries. But like I said, each step of the way, you're gaining ease of use, but you're losing some flexibility. So K-Sql Db has some things that Kafka Streams can't do, but yeah, question?
What percentage of your customers use K-Sql Db? Or
I don't have any numbers, but it's going to be a lot smaller than Kafka Streams. Okay. Kafka Streams is very widely used.
Okay. Kafka Streams Dsl?
Yeah, Kafka Streams Dsl or the Processor API. Those two are used by a lot of, like 80% of the Fortune 500 companies I think out there are using it in one form or another. If you're working with Kafka and if you're using, some people do use Kafka for just a dumb pipe, right? Sending data from using Kafka Connect, bring data in and send it to some other downstream things. But if you're using it for anything significant, you're going to want to do some processing, you're going to use Kafka Streams more than likely.
Sorry to interrupt. We are restarting the router. If that doesn't work, we have a mobile Wi-Fi.
I'm using mine already and he's using his, so I think we're okay.
Okay, awesome.
Thank you, though. The show must go on. The thing with K-Sql Db is, and it's kind of its place in the ecosystem really is for data engineers who aren't programmers. I mean, I don't say not programmers, but they're not Java programmers or .NET programmers. But they eat, drink, and breathe SQL, right? So that's a familiar paradigm for them, and so that's what's being used for a lot of things like that.
Snowblock has an event sourcing platform that's built on Apache Confluent Kafka, and that's basically used to send events between there are systems in the DAX of this cloud. There is an event stream processor which sends
Right.
out to produce level consumers.
Yep. Yeah, it's very commonly used for things like that. And then moving further up the stack, there's a new thing coming out which hasn't been announced yet. Hopefully it's going to be later this year, but they did say I can say it's coming. And this is going to be built on top of all these things we've already seen, but it's going to be purely cloud-based. So you can build your applications in a cloud environment, already pre-deployed, fully managed for you. It'll work on either AWS, Google, or Azure. So it'll be something that'll be part of, probably be part of Confluent Cloud, which runs on any of those three, and on-prem as well. So you'd be able to run these things in a mixture. A lot of our customers have, especially for regulatory reasons, have to have a certain amount of on-prem infrastructure. Even though they're moving most of the cloud, they have to have keep a certain footprint on-prem. And so our stuff is built so that you can integrate between those. So you can have a Kafka cluster on-prem. You can be using Confluent Cloud, which we'll talk about a little bit later on if there's time, and link them together so they work as one virtual cluster. And so the data flows between those seamlessly. So it's really pretty neat. But anyways, this is a new tool coming out. I don't know if the name's even finalized yet, but it's looking pretty cool. So looking forward to that later this year. So like I said, mostly we're going to be focusing here is on Kafka Streams Dsl. So let's take a closer look at that. So as I mentioned, it's just a Java library. You can use it with any JVM language. I prefer Groovy, but anything's fair game. Actually, I'm getting a lot of people using it with Kotlin these days, but probably predominantly still Java. And with it, you define a processor topology, which is a directed acyclic graph of processing nodes. And it has this fluent interface that allows you to connect them, and we'll see some examples of that in a bit. It allows for lots of stateless operations like branching and filtering and mapping. These are all things that are easier to do and fast to work with. But stateful operations are the ones really where you can do some of the powerful stuff. And these are the ones that are much harder to do without using Kafka Streams. But you got counts and aggregates, reduce, and some others. And they're all built in. I'm listing a few here, but these are all built-in functions that you can use, and there's a lot more of them. And each of these will return a Kafka Streams artifact, either a K-stream, a K-table, or a K-group stream, or something like that, which we'll see those in more detail in a bit. And it manages state behind the scenes, like I mentioned. So if you're doing something like a count, for example, you got to store that interim count as you're going. It has to be somewhere, right? So it uses RocksDB by that, and then the RocksDB data stores are individually each backed by Kafka topics using a change data capture mechanism. So that if your application shuts down, because RocksDB databases our data stores are in memory, they're very fast, and that's why you use them for this. But if your application shuts down, you don't want to lose that data. So that it's also written to a Kafka topic. So you restart your application, your RocksDB instances are rehydrated from the Kafka topics. And this is all behind the scenes for you. You don't ever deal with that, but it's there. And one nice thing with the RocksDB is that it allows you can read those data stores yourself. So Kafka Streams have a tool called Interactive Queries, which allows you to read the RocksDB's data stores to get a snapshot of what your current streaming data is looking like. It's Rockset, I think it is. Yeah, Rockset, not Rockset. A lot of confusion on that one. Naming things is hard. And it supports the concept of both streams and tables, which we'll look at in a little bit more detail in a minute. And then you can do joins. So you can join stream to stream, or table to table, or stream to a table. And we'll see some examples of that as well. Now, back to the stream table idea. I want to just go with that a little bit more depth. How are we doing on time? Okay. So streams and tables are basically just two different ways of looking at the exact same data in a Kafka topic. The stream is more closely analogous to the topic itself. It's just an unbounded stream of events. It never ends, and new events keep getting added to it. A table, on the other hand, is the current state or the most recent state of a given key, right? So a table has to have a key. Streams don't necessarily have to have keys. So with looking at we're showing here is a stream and a table, both based on the same input topic. So as we have new events landing in the topic, they're automatically added to the stream, and each new event in the topic is a new event in the stream. But they're only new events in the table if there's a new key. So far there's been 3 new keys, so we have 3 new events in the table. Now we have an update to key A1. So we get a 4th event in the stream, but there's still only 3 entries in the table, but the value of A1 has updated. And so on, right? So it keeps on going like that. And we only get new entries into the table when there's a new key. This will be backed by that, but it isn't. This is actually just a logical concept within Kafka Streams. And also, if you have data that you're working with mostly as a table and not as a stream, then you can change your underlying topic to be what they call compacted. And a compacted topic basically that works similarly to a table where it only guarantees keeping the most recent value for each key. You'll usually have some duplicates as well because it has a cleanup process that runs in the background, but you'll always have the most recent one, and it'll drop off other ones more quickly than normal. And that's just a storage saving mechanism. If you have data going into Kafka topics that's large, you just look up data. All right, and here's another way. I really like this example of streams and tables. So looking at a chess game, right? The moves are a stream. The record of all the moves, each move is an event, and it's a stream of those events. The table represents the current state of it, right? So the board represents the current state. That's like the table. And this is a really good blog post down here at the bottom that you can check out that talks about this in more detail and has some other examples. That's why I borrowed this illustration from that blog post. So that's streams and tables, and they're both very useful for different purposes, and they work together really well in Kafka Streams or K-SQL Db. All right, so now let's take a look at some of the key classes in the Kafka Streams Dsl. The overarching one is just called Kafka Streams, and this is like our application class, basically. It encapsulates a producer and consumer, and it manages the execution of the topology. Streams Builder is what we use to build the topology, and this provides that fluent interface for just hooking things together, the different functions together that we want to use. And we'll see some examples of that. Streams Config is a very helpful class. I want to mention it, but I'm not showing any examples, but it basically just gives you constants for all of the different configuration values that you're going to need to work with when you're working with Kafka Streams. And now here's the artifacts that we work with. So K-Stream, as I mentioned, that represents an unbounded stream of events. Keys are optional. They're based on a topic, so you create a stream based on a topic, and then any events that land on that topic will be in that stream. K-Group Stream, what happened?
On TV,
You got a little Wi-Fi, your Wi-Fi's dead.
Oh.
No, it's just a TV. It's not.
Oh, the TV's having Wi-Fi too. Okay. All right. All right. So the K-Group Stream is a stream of events that's been grouped for aggregation. So whenever you're going to do an aggregation on a stream, you need to do something. You'll make a call that'll group it first, like group by key or something like that, and then that'll produce a K-Group Stream. And then your aggregations or reduces, things like that, will all produce a table. So a count will produce a K table. And the other thing we have is a global K table. So this is a little bit confusing, but when we talk about partitions and the processing of data across partitions, you can have multiple instances of your Kafka Streams application, and they'll each be working off of different partitions in your input topics. And so if you're trying to join a stream in a table and they're not exactly partitioned the same way, then you might not find matches that way, right? So if you're, like, for example, if you're doing a lookup, you're doing a stream to table join, and the table is like a lookup table, like customers or something, you can use a global K table, which will just have all the customers, regardless of what partition they reside in and the topic, and then that will be replicated to every instance of your application. So it will use more memory because it'll duplicate the data in every instance of your application, but it'll make it so that those records are available in all of your application instances, regardless of the partition they're coming from. So it's a little bit confusing, but it's an important tool. When you need it, you'll know, and it's great to have it then. So, and I don't think we have examples of that one in here either. Well, most of our examples will be looking at the K table, the K group stream, K stream, Streams Builder, and Kafka Streams. I think with that, we have some examples. So here's our first example. So here we start off by creating or declaring a streams builder and constructing a new streams builder, and we declare our topology. The topology is what the streams builder will produce, and then we go ahead and put it to work here. So the first thing we're going to do is we're going to call the stream method, which takes an input topic, and then we tell it how to work with that data. So we're going to see this SERDES quite a bit. SERDES are the serializer, deserializer. They're helper classes that have the smarts for serializing data from whatever our format is to Kafka binary format, and then deserializing it from the binary format back to whatever we want it to be. The SERDES classes that we're working with all come with Kafka. Yeah. So we're using this. There's a SERDES class here, which just has a bunch of functions that give you standard SERDES for string, integer, long, double, some things like that. And then this city SERDES is actually, it's not shown here, but it's actually an instance of an Avro-specific SERDES, which is a class that comes with Kafka Streams. And the Avro-specific SERDES will take an Avro class, and in this case, we must have given an Avro class called city, and it will basically serialize and deserialize from your Avro class to the binary format. So we're working with a stream that has a key of a string key and a city for the value. So that's why you have two things here. You always have these in pairs for the key and the value. And then we're going to call on that stream, we're going to call filter not, which is basically just like filter except in reverse. And that takes the key and the value. And then we're going to take from there, we're going to take the value and get the state from the value. And if it equals New York, we're going to filter it out. So we want everything except for New York for some reason. And that returns another stream. So we saw the same stream with the string key and the city for the value, but it doesn't have any New York events anymore. And we're going to call map on that. And map takes the key and the value, and then we can do lots of things with map. Whatever we do is going to happen to every event in the stream. And what we're going to do with this one is we're going to create a new key value pair, and we're going to use the state from the value. State is a field in the value in the city object. We're going to grab the state, use that as our new key, and we're going to grab the population and use that as our new value. So we're creating a completely different kind of stream now. So rather than having a string for the key and a city for the value, we're going to have a state which is still a string. We're going to have the key will be the state, the value will be the population of that city that we just processed. So that still returns a stream, but now it's a completely different stream. And now we're going to call group by key on that. So we're going to group that. And when we do group by key, we tell the SERDES that we're using for the grouping. So this is going to create a new set of data. So we're going to use a string SERDES for the key, which is the state, and then we're going to use the integer SERDES for the value because that's the population now. It's serializer, deserializer, yeah. So SERDES itself is a helper class that gives you serializer, deserializer things for different basic types.
And also the serializer, deserializer, is that the serializing, deserializing to like a JSON representation, or is that actually?
No, this is just going from the type that it is here, like in this case string, to the Kafka binary format.
Okay.
So these are Kafka specific serializers and deserializers.
Okay, so it's not using like the Java serializer.
No.
Okay.
Yeah. See, names are tough. So this call group by key gives us a K group stream. And now K group stream is what has all of your aggregation type functions on it. So reduce, count, all those are on K group stream. You can't call reduce directly on a K stream. So this gives an interim step, gives us a K group stream. On that one we call reduce, and we're just doing a simple sum. So we have an accumulator, and then we have the value coming in. We sum that value, the accumulator plus the current value, and that keeps growing the value. And it's going to be doing this by key though, right? So basically what it's doing here is it's giving us the population, it's accumulating the population for every state. So the end result here is we're going to have the population. What's that?
That's not New York.
I think you said.
That is not New York.
Yeah, every state, exactly. Every state that's not New York is going to get its populations. So we're going to get into the population of the entire state if we have all the cities. We're probably missing some cities, so we may not get the whole number, but that's what this is basically doing. And now this reduce here is going to give us the K table. So this K table would basically, the keys would be the state, the values would be a number, the population, right? So that K table now, we want to write this out to another output topic, and you cannot write a K table to an output topic. So to go back to an output topic, we have to go back to a stream. So we call on the K table, we call .toStream, and then now we have a K stream again, and we call on that, we call .to, which allows us to, I jumped up ahead. Allows us to write to an output topic. Now, when we're doing the two, we have to give it, up here we gave it consumed with different SERDES. Now we're telling produce with these SERDES. So we're telling produce data to this output topic using the string SERDE and the integer SERDE for the value. And that's the whole thing. It's not doing much, but that's just an example to show you the flow. And I wanted to point out specifically how this Fluent interface jumps between data types, right? We start with a stream. This gives us a stream. This gives us a stream. This gives us a group stream. This gives us a table. This goes back to a stream and then writes out to a topic. Once we've defined all this the way we want it, then we call it the builder.build, and that gives us a topology. Now this next line here, I'm just doing a print line of the describe of the topology, and I'll show you why in a minute. And then the last step is to create the Kafka Streams instance. Or this is the actual application part itself. So we create an instance of that, we give it the topology that it's going to run, and we get a set of properties. These properties will include the URL of the Kafka brokers that it's going to connect to, as well as if there's any credentials you need to give it. Usually these days you do. Spring has Kafka support built into it. So they have both for just basic Kafka, and they also have a Spring Stream something or other. So there's Kafka Streams, and both Spring, Micronaut, and Quarkus all provide really good Kafka support. It's pretty good Kafka support. I'm not a real fan of the frameworks support because they lump it into the messaging kind of thing, and sometimes you end up getting a little bit of a least common denominator of all the different messaging tools. But most of them allow you to drop out to the actual client libraries to do things that aren't supported by everybody. All right, so then the next step is just to run start. Once you run start, this is going to basically just, normally you do this with like a shutdown hook or something too to make it so you shut down cleanly. But basically once you call start, you're in an infinite loop. And anytime events land in your input topics, they're going to go through all this processing. And now I mentioned this line here. I put this in here because if you're working with Kafka Streams, I want to introduce you to this really helpful tool that's out on GitHub. And by printing out the topology using this describe, which gives you a text representation of your topology, you can paste that into this tool here, the Kafka Streams Topology Visualizer. And that will, this isn't by Confluent or Apache Kafka. I don't know who wrote this, ZZ85, but it's an amazing tool. And you can use it right on GitHub on that page there. You can paste it into this block here, and it'll give you this visual representation of your topology. I cut it in half to put on the slide. It gives you normally just one straight thing down, unless you're branching, because we'll show branching in a little bit. But when you branch, then this will branch out as well. And that's the thing. Topologies can get pretty complex because you can do branches, and then each of those branches can have its own subtopology that does different things. So it's easy to lose track, and it's hard to reason about it just reading the code. So this gives you a visual representation, which is very helpful for that. So I just wanted to point out that that's available if you start working with Kafka Streams very much. And now there's a few more examples. This example is using a count. So again, we start with a stream with our input topic. We have a key of a string, and our value is a ticket sale. So we use ticket sale 30, which again is going to be a specific Avro 30. And then we call map on that, and we're doing, apparently here, this stream or this input topic doesn't have a key. So this string key here is going to be null at first. So we're going to call map on that, and we're going to create a new key value pair where we will get the title of the probably guess it's a movie ticket sale. We're going to get the title from the value and use that as the key. So the value will still be the same, but the key will now be the title. And so that title value, that's going to be value. The title is going to be duplicated both in the key and in the value, but that's okay. So now our stream has a key and a value, and we're going to call group by key. So we couldn't call group by key if we didn't have anything in the key. If the key was null, we call group by key. We would get one lump of, it basically wouldn't do anything. So now we're grouping it by that title, and we're using the SERDES to group it, which would be the string SERDES and the ticket sale SERDE. And now, this could still have duplicates. There are ways to prevent duplicates. That's usually on the producer end. I don't go to it in this talk, but there's an idempotent producer. Actually, I think I do mention it later when we talk about exactly once semantics. But idempotent producer will set it up so you don't produce duplicates. So then on the group stream, we can call count, and that will give us a K table. And again, we're turning that back to a stream. We're calling map values on that. And map values is like map, except it only changes the value. You can't change the key with map value. So we just pass in the value, and we're taking that value, turning it to a string. So remember, the value when I was an integer is the number of ticket sales from the count. And then we're adding the string tickets sold. So this is going to give us a running count of the title. So whatever movie, 10 tickets sold, 12 tickets sold, 20 tickets sold, like that. And we'll write that to an output topic. So this might be our movie sales dashboard we're feeding here. So that's counting. And here we mentioned branching earlier. Branching allows us to split events into multiple streams, or split one stream of events into multiple streams. So first we start out by declaring an array of K-streams. We're not going to have just one K-stream here. We're going to have an array of them. And we're calling that branches. And we're using the builder to create that. We call it builder.stream. So this first stream is just a single stream that we're creating. And then we're calling branch on that. And this branch is going to give us 3 different streams. And that's what's going to feed into this array up here. So the branch function just takes some number of predicates, as many as you want to give it. And for each predicate, it will find any events that match that, and it will load those into that branch. And it starts from the top and works its way down. So if it's found in the first one, it can't be in any other ones downstream, right? It's going to, each event can only be in one branch. So this one we're looking at the genre of the movie appearance, the acting events. If it's drama, it's going to go in the first branch. If it's fantasy, it's going to go in the second branch, and everything else will go in the third branch. So this, just giving the predicate just true is the equivalent of a default in a switch statement, right? So everything else, this isn't necessary. If you only want drama and fantasy things, you can leave this off and you'll just get 2 branches and you'll have those 2 things and everything else will be ignored. It's key thing to remember when you're working with Kafka Streams is that your input topic never changes, right? That's immutable. So if we drop this out and remove this last one here, we would lose a lot of events in the branches, but those events aren't gone. They're still in the original acting event input topic, right? So your input topics are never affected by whatever you do downstream here. All right, so now we have 3 different branches, and now we can refer each of those out to a new output topic. So basically, we took one topic, we split it into 3 topics using this little bit of code here. Now, we don't always just do this. Like I said, you can branch, and then from your branches, you can have different things that you do with each of those branches based on the data in them, right? Say for drama movies, we want to send those off to some other process to be published in our drama newsletter, and fantasy topics, we want to send those off to our Twitter stream for our Comic-Con thing coming up or something, whatever. There might be different processing you do based on the data in the branches, and so this is where your topology can start splitting out into multiple subtopologies. So branches is powerful, but branching can be confusing. So, and it's one of the things I mentioned earlier. If you compare Kafka Streams to K-Sql Db, that's one thing that you cannot do in K-Sql Db. There's no concept of branching in K-Sql or in SQL at all, so you can't do that there. It's branching, now joining a stream in a table. This is kind of a fun one. So here we have a stream of movies coming in, and we're using it a little bit different. Rather than the consumed with, we're giving it the data types. And what happens is in this application, this one we actually have the code for if you want to look at it a little more deeply in a minute here, because we're almost done. The default SERDI for values in this application is the specific Avro SERDI. So anytime that it encounters an Avro class, which is movie here, this is an Avro class. So it's going to see this Avro class as the value and say, oh, okay, I'm going to use the specific Avro SERDI with this class. So what's the word? Implicit typing there. I'll show you how that's set up in a bit here. So we take this stream we're creating using the stream method on the movie topic. Now the movie topic doesn't have a key to start with, so we're going to call this map again and do the same thing we did earlier, where we create a new key value pair. We're going to get the movie ID and use that as the key, and the value will still be the movie. And then we're going to take that stream and write it out to a new topic called rekey movie topic. And the reason we're writing out to a new topic as an interim step here is because what we really want is a K table, and we don't want to do any kind of aggregation to get it. We want to add the key to this. We have a stream with no key. We can't make a table out of a stream with no key. Right? A topic that has no key, you cannot create a table from it. So we're going to rekey it, and then we're going to write out to a new topic, and this topic will have a key. So now we come down here and declare a K table, again with a key of string and a value of movie, and we're going to call builder.table, which works just like builder.stream, but it takes a topic that has to have a key. And so it's going to take our new rekeyed movie topic, and now we'll have a K table. So our K table here is basically a lookup table. It has all of our movies in it. And now we have another stream. This is rating. So our customers are rating the movies as they're sitting in the theater or watching it from home. They're on their phone. They're sending in ratings into our ratings application, and we're going to feed those into the stream here. So this stream is going to have a key of string again and a value of the rating. And again, when they're coming in from the application, there's no key. So we're going to call this map again and grab the ID to set that as the key as well. And this is the same ID that the movie is using, so they can use that to link those up. And that will be used in the join. So the key is going to be the movie ID. The value is going to be the rating. And now we create a third stream here. And this one we're not going to create using stream. We're going to create it using join on the rating stream. So K-Stream has a function on it called join, or a method on it called join. And so we're going to call ratings.join, which takes another either stream or table. In this case, it's taking the table, the K-Stream that we created up here for movies. Yeah, this one. Sorry, what's that?
Where's join?
Right down here, ratings.join.
Yeah, movies, joiner. Where's joiner?
The joiner we'll see in a minute. Yeah, I was going to get to that. So you jumped ahead of me. So the join takes another set of data, either a table or a stream to join on, and it takes a joiner class, which is something that we create and actually have it on the next slide. Basically, the joiner class just tells which fields we want from each of these components. Right? So we do the join, and that creates a new stream, and we're going to write that out to another topic. And then this one's kind of cool here. We're going to produce this with a string sturdy for the key, and a rated movie avro sturdy, which is something, it's a method that we're going to call, and I'll show you that method in a little bit here, which basically takes the specific avro sturdy, feeds it the rated movie class and some properties, and it creates an avro sturdy for us, just like the movie sturdy up here that's done implicitly for us. This is just showing a different way of doing the same thing, and I'll show you the code for that in just a bit. But first, here's the value joiner I mentioned. So it just takes in the rating and a rating and a movie, and then it tells you which fields we want from each of those to give us our rated movie object. And trying to run late on time, but so this is, I want to just give a quick example. Windowing is a very complex topic, which I'm not going to go into real in depth here, but it's something that's very useful in Kafka Streams, specifically with joins or with aggregations. So we're doing it here with an aggregation. With joins, you might use windows to give a time block for your join to occur. If data, especially if you're joining two streams. If you're joining a stream in a table, usually you don't need windowing because the table's more static. But if you're joining two streams, the event that you're trying to join with may not have occurred yet, right? So you want to leave a window of time for that to catch up. So that's what using joins. Here we're using it for an aggregation. It's very common in aggregations because you want to get counts based on a certain chunk of time, not just every time something comes in. So we'll skip all this first stuff, which is the same thing before with the mapping and then group by key. And now this new one here is windowed by key. So we have a K group stream here, and then the K group stream has a method on it called windowed by, and that lets us give a duration that we're going to window by. And that says, okay, I know an aggregation or something like that is coming up, and we're going to window it. So what duration are we using? So we're going to set it for 10 minutes, and then we call count. And now the count will work on this group with this window duration. So it's going to give us a count every 10 minutes. So this will emit a value every 10 minutes rather than every time a new event lands. If you use it without windowing, every time a new event lands in your input topic, you get a new count coming out. So the count just keeps increasing, right? This gives you a count by a chunk of time. So every 10 minutes, we'll get a new value coming out with the current count, and then we'll write that out to a stream. So the windows, this is just a default window, which I believe is called the Tumbling Window. Tumbling Window has a duration, and it just gives you 10 minutes of data, and then it jumps over to the next 10 minutes of data, and the next 10 minutes of data. There's no overlapping. You can also use what's called a hopping window, which has a duration and an advance time. So you can have a duration of 10 minutes, but an advance of 1 minute. And what that'll do is that'll give you a new value every 1 minute, but it'll give you 10 minutes worth of data every minute. So then you'll have overlapping. And that's very commonly used for feeding dashboards, where you want the value to be updated frequently, like maybe every minute or every 10 seconds, but you want the data it's showing to be the last 10 minutes worth or the last hour or whatever it is. So that was when you would use a hopping window. Or there's also a sliding window, which works similarly, but moves more incrementally. So that's windowing. Just wanted to touch on it briefly. So there's a lot more to that if you want to dig into it deeper. And then I want to mention exactly once semantics, which is very important in Kafka Streams applications, especially like things like financial applications, where you can't have something happening twice, right? If someone sends a message, they want to send some money to somebody, you don't want that to happen twice, and then it's sending double the money. So exactly once is handled through Kafka Streams. I'm not going to get into how it all works, but I want to show you how easy it is to use. There's a configuration on your Kafka Streams application called processing.guarantee. You set that to equal exactly once. And then what that will do is that will automatically on the producer, remember Kafka Streams application has an underlying producer and consumer behind the scenes. So it will set on its underlying producer, it will set enable item potence to true, which turns this into an item potent producer. It sets the max in-flight request to 1, because if you have more than one request at the same time, then you could end up with duplicates if there's a retry happening. And then it sets the retries to max value, which is kind of an optional thing, but it's a good way to handle it, just so you can, if something fails once, you can retry it until it actually does occur. Because this isn't like at least once, it's exactly once. You always want to make sure everything does occur. And then it sets a transactional ID, which triggers the Kafka transaction handling.
So why would I choose to have that exactly once option enabled all the time, or for every application?
Because some applications don't need it, and it is a little bit costly on the processing side. So you can run a lot faster if you're not using it. And so if you're working with something like, in fact, a real common thing with Kafka Streams is to handle things like syslog data or clickstream data, and those things don't usually need to be handled with that type of consistency, right? So if you lose some, or if there's some duplicates in processing of a clickstream, it's not, you're trying to get your number of clicks on your website per day or whatever like that. It's not usually that critical. So, but it depends on your use case. It is becoming used more and more. And it was a tough problem to solve, and a really important one that really opened up the door to using Kafka Streams for a lot of use cases where it couldn't be used before. But it's been in there about 3 or 4 years now, I think.
So if the producer attempts to send the same event once more, what exactly once?
Yeah, so one of the things it says is it turns on the Kafka transaction handling. And so when you're producing within a transaction, if the transaction fails and then you repeat it, but then that original transaction picks up again, starts to try to happen again, that's so you can do duplicates, it'll recognize that and it'll block it. So if it tries to send a second transaction again, it'll either throw an error, or if it's already processed the other one successfully, it'll just ignore it.
So we had point of sales events like return was paid. So events like that, but that is
Right.
when the tax return was paid in the office, they would have like a POS event fired. So I think that we would use that.
Right, they probably would use that for that.
And I think this is maybe also time was just I may have missed some of it, but with also like duplicates, like you may want to have like say multiple brokers just to have like redundancy and backup. And like how does that handle where it's like you're talking to one broker, it went down, he calls the backup, like how does that handle so you don't actually do like duplicates or something like that?
Yeah, the way the brokers are handled using the replication model, which each broker will have a replica of the topic, but the lead broker will be the one that's doing all the work, especially all the writing. You can read from follower brokers as an efficiency, but I don't think you can actually do that with transactions turned on. So a lot of it has to do with that. So when you turn on transactions, you set a flag on the consumer, which I was going to show next, where you set read committed. So you're only going to read things that have been committed in the transaction. So if a broker goes down in the middle of a transaction, the new broker will pick up, and that transaction will be aborted because the broker went down. So it'll be retried, and then picked up again. And the new broker will handle the transaction all the way through. Okay. And so if anything, if the other broker came back up, they call it a zombie. And now if it tries to read from that, it's fenced off. And so you go, because it uses an epoch. So it sets that, increments that when the new one takes over and says, oh, you're an older epoch, we're not going to listen to you. And so there's a lot of safeguards built into that.
Okay, yeah. The only time I've kind of worked with Kafka is like some like POC stuff, and so never kind of got to like man, yeah, you probably would have had one at redundancy, but how do you make sure you don't accidentally
right?
do much?
The default stuff with Kafka, you can get duplicates. So the key thing they're trying to, the key thing that the default configurations of Kafka focuses on is not losing data.
Yeah.
So we focus basically on the at least once processing, right? So everything that comes through is going to be processed at least once. You might get duplicates. If you don't want duplicates, you want exactly once, then you can use these semantics here, and it does more work. It does, like I said, slows down some of your throughput because the transaction handling will block some of the parallel things you could do otherwise.
So how is at least once?
At least once basically means that you set your producer to retry. And so whenever a producer tries to send something, if it fails, it will just keep retrying until it finally is able to get through. Now, with that set that way, and you can set the limits. Like I said, it sets the retries to max value, so huge, right? You can set lower numbers for retries, and you also can do things where you, at a certain number of retries, if it doesn't work, you send that off to like a dead letter topic or something like that. So there's different ways you can handle that. But the default will just keep retrying until it gets through. And then with that, when that happens, you could end up with a situation where it finally gets through, but the other one that was taking longer didn't really fail, but it was taking longer, it gets through as well. And that's how you end up with duplicates. And there's a really great blog post on exactly once and how it's implemented and stuff like that you can check out there later if you'd like. And K-Sql Db, I'm going to go through this kind of quickly, so I wanted to show the code from some of the other stuff we looked at earlier, since I was mostly focusing on Kafka Streams. But so K-Sql Db is a database purpose-built for streaming applications. Some people argue whether it's really a database. It's not a database like Postgres or MySQL, it's right? Not a relational database. But if you think of a database that's consisting of compute and storage, then it really kind of is. The storage is Kafka topics, but the compute is this streaming engine, K-Sql Db. It's built on top of the Kafka client libraries and Kafka Streams. It runs in its own cluster. That's one thing that's different. It's not a library that you can include in your applications. It is its own application, so you have to communicate with it. But you can create streaming applications just like you could with Kafka Streams and doing most of the same things, but using SQL. And there's a native Java driver, so you can interact with your Java applications and K-Sql Db, so you can send queries or create new queries through that driver through an API there, or you can retrieve data. So you can feed the data from your those continuous queries I mentioned. You can feed that back into your Java application, do something else with it. Or you can use a REST interface for other languages. And the idea is that you can do a lot of stuff with it with less code than you could with the Java application. And that might be debatable, but. And here's in this example, it's actually not that much less code, but here's an example just to show how they handle things differently. With Kafka Streams here, we would create a stream from our input topic, and this is going to be publications. And we're going to filter for the name of the publication, or the name, we're filtering, and okay, so name is the key, I guess, and publication is the value. And we're filtering to see if the name of the publication is George R.R. Martin. I guess it'd be the author's name, I don't know. Anyways, and then we're writing that back out to another topic. It's just gonna sit there forever, yeah, and it's frustrating, I know. So that's in Kafka Streams. In K-Sql Db, you would create a stream on the main topic, publications. If it's using Avro, for example, or JSON schema or protobuf, you can set that here, tell what value format is, and it will use that will use the schema then to determine the fields, so you don't have to declare any fields. Oh, I'm sorry. Yeah, that's I should have mentioned that earlier. Avro is it's Apache project. It's a data serialization format. You declare it using something like JSON basically, but then it creates a binary format that's much lighter weight than JSON. And so you can use it with Kafka, but you can also use, it was originally invented just to use as a faster transport when you're sending data across HTTP, since JSON's kind of wordy and better than XML, but still a lot of text. And the Avro will turn that into a binary format that's much lighter weight or much tighter. So if you're using that, it will get the field values from that. And then I'll show you an Avro schema in just a bit here. And then you create another stream. This stream is based on a select. So we're going to select from publications with a name equals George R.R. Martin, and we're creating a new stream from that. And that's why you create these things. And rather than doing create the stream and then call filter on it, this creates a stream and then uses a select to do the filtering. And that's a pretty common pattern in K-Sql Db. Another example here, and I think this is the last one for this, is joining 3 different streams together. And this is one thing that's more difficult to do with Kafka Streams because you can only join 2 things at a time. You can stack those and join a bunch of them that way, but you have to do separate calls. So this allows us to join, we're joining our users, our clicks, and our codes together. And this would be like our value joiner where we tell the fields we want from each thing. And then we're selecting those from clicks, the left join on codes, using the status, which is also called codes, and then using the join on users using the user ID. And you see also we have functions like cast, where we have to cast our status, which is a string. We're going to cast that as an int to match up with the codes in the codes stream. So it's joining 3 streams, and it's going to give you one new stream called clicks enriched. So that's K-Sql Db. Okay, so now I wanted to real quickly, I was getting a little bit late, I wanted to jump over and show you some of the code we were just looking at. So the thing with the movie ratings, I actually have this as a full application here. And so this is what we look at for the topology here. But I want to show you how it does this thing. Right here we just put movie, and it gives you the whole, it gives you that Avro specific SERDI. And it does that by down here. Well, I'm going to show you here real quick. What we do is it's in our configuration somewhere. Where did it go? Oh, here it is, right here. So in our properties, we're putting in the default key SERDI and the default value SERDI. The default key SERDI is string. So if it finds a type of a string, it's going to just use that. And our default value is specific Avro SERDI. And this uses those Avro classes I'll tell you about, and I'll show you one of those in a second here. It uses those, and it will just create a SERDI for us that will serialize and deserialize using that Avro class as the mapping, right? And it does that up here just by picking up the fact that we said we have a value type of movie, and movie is an Avro class, which is right up. Well, that's the Java version of it. Where's right here is the Avro class. So again, you write it using JSON, but you just give it the type as a record, the name is movie, and here's our fields. Right? And so when we're serializing and deserializing, it's going to use that and the Avro specific SERDI and this Avro class. So use those together to do a serialization and deserialization for us. And that turns into a Java class here, which is really hairy, but Gradle builds that for us. You don't have to do that. And that's one way of using the Avro specific SERDI. The other way is that one that I showed, the second one, where actually we had a new function here, or a new method. Where did it go? Someone stop me when you see it. Oh, here it is. I was already on it. So right here we have this method here called rated movie Avro SERDI, which returns a specific Avro SERDI, which is the same thing that we would get automatically using that class, like I just showed you. But here we're going to create one specifically. We're going to tell it the type's going to be rated movie. That's the Avro class, and it's actually not on GitHub, but where it is, I'll show you in just a second. But so this is just another way of doing the same thing. When we're doing it this way, we have to pass in our properties. So it's a little bit more involved here, but it's another way of creating an Avro SERDI to use for serializing and deserializing your data. But I think that we could have just done up here is instead of doing this, we could have just given the types up here for the rated movie. We could just declare it with the like this string and rated movie down here, and it would have done the same thing using the specific Avro SERDI. Okay, so that's just want to show you those things a bit. And then of course here is also our, where did it go? Our movie rating joiner, right? So that's a class we showed on the other slide. Okay, so where this is all at is right here. So if you go to developer.confluent.io, we have these tutorials, and you can just search for it. There's one called join stream and table, and in here is all of that code that we just looked at, and it's really cool. I love it. I wanted to show you because I love these tutorials. When I was first getting started with Kafka, I spent tons of time on these. There's a bunch of them out there, several dozen of them, I think, and it gives you step-by-step everything you need, right? So right now, creating your directory to work in, setting up, you can use Docker or you can use Confluent Cloud. This is the Docker version here, so it gives you a Docker Compose YAML file that'll spin up all your infrastructure. So it'll spin up your, right now, this will spin up Zookeeper, which Kafka still uses for a little bit longer. It'll spin up Kafka Broker and a Schema Registry instance. So which works with the Avro classes, those Avro schemas we talked about earlier. So you run your Docker Compose with that. That gets up and running. Then it gives you a Gradle build file. So you can create that, and then set up your configurations for properties file, and right down to there's your Avro classes. It gives you all those. So all this can be done with just copy and paste step by step if you want to run this. I ran through this whole thing and it took me about 6 minutes to do the whole thing, and just copy paste and then build it and run it, and it works. And it's a great way to see it in action. And then what I do when I was learning, what I would do is I would run these like this, and then I would go back and change things and see how it affects stuff. And it's really, I just think it's a great way to learn these. So I wanted to show this off a little bit. But that one I was just looking at an idea was just from this. That's why I didn't put it on GitHub, because this would be a duplicate of what's already here. So here's the main class here.
There's a question on YouTube that says, Dave, what are you doing? Dash test how?
I think that was when the Wi-Fi went out.
Okay, never mind.
Oh.
I thought you might know this guy, Dave.
Bill Gottschalk.
What is it?
Bill Gottschalk. G-O-T-T.
Oh, I know Bill.
Yeah.
I don't know where I know him from, but I know him.
I think he's pretty active in kind of job in community.
Okay.
Definitely here. He's usually been a pretty regular before.
I know that name. Yeah. All right, so I just want to show that. That's why I could have put that up on GitHub, but it's just all right from this project here. So, and so I said, like, you can get to that. Where's that?
So I have a question. Like in 2010, we designed enterprise service bus, and we built it on.
Ouch.
It's cool. I'll say it's built on ActiveMQ and Camel. If we were doing that today, would we use Kafka?
I would, yeah. It does a lot of the same things. And I have a different talk that goes over the whole Kafka ecosystem. There's a lot of things in play with Kafka. Kafka Connect is a real key piece of that. There are Kafka Connect connectors. What Kafka Connect basically does is it takes the producer and consumer, and it bundles those in, and then adds on these plugins. The plugins know how to talk to other systems. So you'll have a source connector will know how to read from MongoDB or Oracle or Excel or Jira, and it reads from those sources and then just produces to Kafka. And then the consumer, you have a consumer that would for a sync connector, it'll consume from the Kafka topics and use a plugin to sync out to any external source. So like Elasticsearch or S3 or there's hundreds of them out there. So, and you can also create your own if you have a custom data format. So that would replace a lot of what you would use for your ESB. That plus Kafka together would allow you to build out a lot of those same things. And then in between, using things like Kafka Streams to do any processing along the way. So yeah, it's together. It really is an event streaming platform that allows you just to do almost anything you need to do with the data in your application, the data in your organizations today. And I think that's all I had, unless there's any questions.
One thing I was kind of curious about is when it comes to testing, I guess there's two things. Like, does Confluent like keep like a container for like doing like test containers, like any sort of library, or are you familiar with test containers?
I'm a little bit familiar. One of my former coworkers, used to use it a lot, Victor Gamoff, and he talks about it a lot. But I never used it myself yet. But I've heard it's really great. And I think you use like a Docker image with that, or how does?
Yeah.
So Confluent does provide a bunch of Docker images that you can use for things. That's what we're using in this here with the Docker Compose thing. So you can pull down those images and use those with those types of tools. As far as testing Kafka Streams application, there is a handy thing to just show real briefly. So one of the things with these tutorials is they all include testing.
Yeah.
So after we create our topology, do also like that, we can actually run it, and then we can test it.
They could never file like a test event or anything like that to make sure that all the processing is working fine. So we just used to mock the method.
Yeah, you can run, and we've seen some people that will run a parallel environment. So you have the whole application running in a test environment, then you can run test data through that. But testing through the live one is going to be kind of tricky. But testing while you're coding, Again, all these tutorials will have a testing section on them, and so it uses this. Where did it go? Oh, this is the properties. There's yeah, here's the topology test driver. Comes with Kafka Streams and allows you to help build out unit tests that will basically fake out topics and use lists for topics and things like that. So it allows you to run a lot of your tests that way. Test containers I've heard is an even better method, but this is one of the standard thing that comes with Apache Kafka is this topology test driver. And
so is that? Can you zoom in?
oh yeah.
I can just look at it on my laptop since I'm pretty cheap. I guess, or I don't know, is this also maybe using something like contract-driven testing? So, like a while back when I was kind of working with it, there's like a library called Spring Cloud Contract, and there's like also another one like called Pact, I believe, that's kind of more generic for, I think even outside of Java.
Yeah.
I know with Spring Cloud Contract, one issue they were running into is how to kind of simulate publishing. I don't know if that. So just to explain quickly what contract-driven development is like you can write out like, given this kind of message, I should expect this kind of response, or if I get this kind of message, this is what I should do with it. Which would be really great because like you can simulate stuff without having to spin up environments or something like that. I just didn't know if there's been any improvements in that area or not, or
yeah, I don't know of anything specific. Yeah, so I don't know anything specific on it, but these things do show some examples of how to do the testing with Kafka Streams.
Okay. Yeah.
And one of the things it does have, I'm trying to find it here. Yeah, so it'll use lists to mock basically the topics, and then it handles the publishing for you as well to the input topic. I'm not exactly sure how, but if you scroll through that, you should be able to find where it's doing that.
Yeah.
So, and as far as improvements, I don't know, but the current state is what you'll see in those things there.
Okay. Cool.
How does Kafka handles like data encryption or security? Say if I'm dealing with like sensitive data, patient data, or kind of some user data, how Kafka is dealing with that?
Well, it deals with however you do, right? So you can encrypt your data as you're writing it into Kafka, so that when it's in Kafka topics, it's encrypted, and then decrypted as you're pulling it back out again. If that's the most common way to do. If you're using Kafka Connect, somebody just wrote recently an encrypting connector which will do field level encryption of your data as you're writing it into topics. But there's different ways to handle that. Other ways is just encrypt the storage at the storage layer where the drives where the topics are stored. That's some people handle it that way. And then as far as this, security, there's all kinds of different security mechanisms you can use on your Kafka brokers. When you create them, when you spin them up, you set all that in the configuration. Yeah, when it's in the topics, it's in a binary format, but it's not encrypted, and people who know how to serialize it can take that data and deserialize it. So if you want it further encrypted than that, you could either encrypt the drive that it's on the brokers, or you can encrypt it before you send it in. So
Earlier,
other questions?
Having a replication ability, does it have a solution for being able to keep instances in sync across different data centers in real time?
Yeah, there are multiple ways of doing that. There's in fact there's a I don't want to do that one. I want to go to this one down here. Kafka Internals is this course we have here. These courses are great. There's 10 of them out there right now on all kinds of topics, including one on Kafka Streams. But this one's on internals of Kafka, and it talks about, there we go, georeplication. And so there's multiple forms of georeplication.
Remember when I'm using it, it's really small.
Oh, I forgot. Yeah, okay. So There's different ways to handle it. There's the multi-region clusters is one way to set it up. There's Mirror Maker 2, which is an Apache project that allows you to link two different clusters and keep them in sync. They all have certain drawbacks with things like offsets being in sync and things like that. And if you're using Confluence tools like Confluent Cloud or Confluent Platform, we have Confluent Replicator, which works like Mirror Maker 2, but enhances some of the things like keeping track of the offsets and things like that. And then our crown jewel right now is we call cluster linking. This is what I was talking about, where you can have two clusters in different data centers, or you can have a cluster in a local data center as well as on Confluent Cloud. Have a cluster there, and you can link those together so they'll act as one. And all of the offsets, all of the topics, it all stays in sync. So, and then you can. For Kafka, there are a couple. The main ones right now would probably be Pulsar, and which is it's another Apache project. Yeah, Apache likes to cannibalize itself a lot. So, but that's one that's it's much smaller in scale as far as adoption. It's like way down there, but it's growing, and some people like it. It's got more pieces to it. Like we have Kafka currently relies on Zookeeper to handle some metadata stuff. That's going away pretty soon. So Kafka's going to use Kafka for its own metadata, since it's pretty well structured for that. It's a new Raft protocol they're built in. But Pulsar uses Zookeeper, Pulsar itself, and I think also uses Bookkeeper. So it's like multiple pieces you have to run to be running Pulsar. So there's some disadvantages there. Obviously I'm biased, but there are people that do like Pulsar. That's one competitor. The other competitor is Red Panda, which is basically a Kafka clone written in C++. So it doesn't have the ecosystem around it, and so you don't have things like Kafka Streams or things like that. But for the brokers itself, it's a competitor, and it's a lot faster because it's written in C++. So those are the main competitors there. As far as competitors to Confluent, there are a lot of other people. Since Kafka is open source, Apache, a lot of Amazon has their own MSK, which competes with our Confluent Cloud. There's other smaller groups that do hosted Kafka. It's not fully managed. So one of the differences with Confluent Cloud, which I think I had a slide on that back in my slide deck. Let's go back to that real quick. Oh, where's my slides? Oh, it's right there. Okay. So yeah, that's Confluent Cloud. I borrowed this slide from the last time I was presenting at the No Fluff Just Stuff conference. So if you wanted to use this promo code, you get $200 of free credit for Confluent Cloud if you sign up for a trial for it. But anyways, on Confluent Cloud, it's a Kafka as a service. So you don't worry about brokers at all. You create topics with how many partitions you want in them, and then you start sending data to those topics. You attach your clients. You can use Kafka Connect. It's hosted as well. Your applications like Kafka Streams or consumers and producers, those would still be your own thing you run somewhere else. You're usually in the same cloud, but it doesn't have to be. But all of the infrastructure is handled for you, and you don't have to. So like with some of the other ones, it's a hosted Kafka where they run a set of brokers for you. You tell them how many brokers you want, how much memory, what size of disk you want, all that stuff like that. With Confluent Cloud, you don't do any of that at all. It's just your topics, and as much space as needed, and you basically pay for what you use. So I think it's a really easy way to use Kafka. It has the advantage. Docker is also an easy way to use it, just for trying it out. But the problem with that is when you shut that down, everything you did goes away. So with Confluent Cloud, you can just real quickly create a few clusters or a few topics on your virtual cluster and start using those, and the data is still there. If you come back later and want to try some more stuff, your data is still there. So that's what Confluent Cloud is. Basically Kafka as a service. Yeah. And I said, so you can use that code if you want to get a discount or some free credits on that. I also want to show you there's a couple of books out there that are really great resources on Kafka Streams. This one actually changed. This was the second edition of Kafka Streams in Action, which Kafka Streams in Action is an excellent book for learning Kafka Streams. Bill Bajek is one of my coworkers, a really smart guy. And what? Oh, Manning's early access program. So he's working on the second edition of the book, and it's still in early access. And they were going to change the title to Event Streaming with Kafka Streams and K-Sql Db, but decided just to stick with Kafka Streams Action second edition. So this is title. This cover's out of date, but the book is still coming soon. This is a book that's already out in print. Mitch Seymour works at MailChimp, and he's done some really cool stuff with this. Also, if you have kids and you want them to learn about event streaming, Mitch Seymour wrote this really cool book called Merrily Down the Stream. Have you seen that, anyone? What?
Oh, just merrily down the street.
Just the concept of it. Let me find it real quick to show you. It's really cool. Get to a browser again. Or is it gently? Makes gently down the stream. Yeah, it's with otters in a stream, and it really does really well. It does a really good job of explaining Kafka and event streaming using these otters. They send messages down by sending them in these bottles down the stream, and then they.
Isn't there someone that also did something like a children's book for Kubernetes?
They may have. I haven't seen that one.
So.
This guy and another guy, Martin Kleppman, are working together on one to describe encryption. So yeah. Anyway, that's a really cool resource. But yeah, I think that's all I had. I think we're over time a little bit. So should I shut this down? Okay, you can do your announcements, or you can have this back.
It's mostly for the guys here. On Saturdays between 9 and 11, we have Operation Code, which is a national organization that gives veterans who want to be in IT. If they have 1 hour of their GI Bill left, they can subscribe to a vet tech program and go through boot camps. I mean, we have very successful people that didn't know anything about coding, and now they're making $80K a year. So it's really cool. And we have a nice mixture of people who are veterans and want to code, and